Hello, welcome back, everyone, to Learning as a Hobby. I'm going to do the exercises for, or some of the exercises for Taylor's classical mechanics in this video. There's only 3 of them that I do. There's not that many problems in the section, so I'm just going to jump right into them. We'll do the first, second, and third question in the section. So starting with the first 2 questions are actually on just solving simple differential equations. So 124 says find the general solution of the first order equation df dt equals f of t for an unknown function f. How many arbitrary constants does the general solution contain? So this is just a linear first order linear differential equation. So in other words, dy dt equals y, which is separable. We've actually done a million of these already in the Simmons book, so hopefully by now you guys know how to do this. So separate your variables, find the family of integral curves, and you get a one parameter family of solutions, y equals c e to the t, right? That's the general solution, and it has one arbitrary constant in it, so it's one parameter family of curves. Question number 125 is a similar question, but with just a slightly different differential equation. They want you to solve df dt equals -3f. So again, going through the same process, this is a separable differential equation. So separate your variables, and you end up with ln absolute y equals -3t plus c when you take the integrals. And then when you simplify, you get y equals c e to the -3t as the general solution. So again, you get a single parameter family of curves as the general solution. So that's half of the questions in the chapter. So 126 actually has a bunch of parts to it. So this is the last question I'll do in this section, because the next one is relatively similar. It deals with inertial frames, and he just asks for like a qualitative solution. So I'll just do this one because he asks for actual analytic answers. So question 126 says, I'm standing on a level floor at the origin of an inertial frame, S, and kick a frictionless puck due north across the floor. So part A says, write down the x and y coordinates of the puck as functions of time as seen from my inertial frame. So if we set up our coordinate system, put the puck at the origin at time t equals 0, we can write down the set of parametric equations for the x and y coordinates in terms of time, where time is positive, so starts at 0 and goes up in value. So then since we're kicking the puck straight north, so straight along the positive y-axis, that means that x stays constant at 0. So the x coordinate is always x equals 0, and y is equal to ct, where we're imparting some velocity to the puck, some initial velocity to the puck. So y equals ct. In other words, the velocity of the puck is constant. So because we're not moving, and etc. So the constant c is positive because it has to move along the positive y-axis because we're kicking it north, and that's it. That's the representation for the x and y coordinates, right? Then he has another part to the same question, but separate question. Now consider 2 more observers. The first at rest in a frame S prime that travels with constant velocity v due east relative to s. The second at rest in a frame S double prime that travels with constant acceleration due east relative to s. All 3 frames coincide at the moment when I kick the puck, and S double prime is at rest relative to s at the same moment. And for part B, they ask, find the coordinates of x prime and y prime of the puck and describe the puck's path as seen from S prime. Okay, so y prime stays the same. It's still going north at constant velocity. So y prime of t is c times t. But x prime now is no longer 0 because the reference frame the reference frame S prime is going to the east as time increases, and the reference frame S prime is moving with constant velocity v. So that means that the x coordinate is going this way of the puck as time, in the opposite direction. So it has opposite direction, but with the same velocity as the reference frame is moving with respect to the reference frame S. So x prime is given by negative vt. And again, t is greater than 0. And if you want to know what the shape of the path looks like from S prime, you can just solve for the parameter t, and that gives, oh, sorry, there's a typo here. There should be x. This should have been x prime here. Right, so what the path looks like y, the straight line y equals negative c over v x prime. So in other words, if this is s reference frame S prime, this is Y prime X prime, the puck looks like it's going like this, right? Where the slope of the line is negative C over V for, as time increases. So that's the trace of the parametric path, or the path in the curve, right? It's going like this, the puck, as time goes on. Right, so the puck moves along the straight line to the northwest with respect to the origin of S prime, right? And then for the next part C, they want us to do the same thing, but for the reference prime. I keep saying reference prime. The the reference frame S double prime. All right. So here again, Y double prime is the same thing. It's still, the puck is still moving north with constant velocity c. So the Y coordinate is given by c times t, but the reference frame the reference frame x double prime is being accelerated at a constant rate going to the east. So here, that means that x double dot is constant, so it's being accelerated at some constant velocity k0 going well, the value of x prime of the puck would be going in the opposite direction that it's the reference frame is being accelerated at. So if the reference frame is being accelerated this way at constant velocity, constant acceleration k0, then the x coordinate of the puck will be going in the opposite direction. So that'll have acceleration negative k0, and then you could anti-differentiate, and you end up with a quadratic function in the time, in the variable time for the x coordinate in terms of S double prime. But they said that the reference frame S double prime starts at the origin, so k2 is 0 with 0 velocity, 0 starting velocity, so k1 is 0. So that means that the x coordinate, let's erase this. That means that the x coordinate of the puck with respect to reference frame S double prime is this quadratic function in time. Okay, and then if you want to eliminate the parameter to get what the shape of the path looks like, you can do that. So for example, we can solve for t in the second equation because it's 1-to-1. And we can substitute this, we can substitute, sorry. We can substitute this in for t in the equation for x double prime. So that means that x double prime of t is given by negative k over 2 times y double prime squared over c squared. And then if you rearrange things, it looks like negative k over 2 c squared y double prime squared. So in other words, you get this half of a parabola that lies on its side. So the puck looks like it's moving along that part of the parabola. And that's what the path looks like for reference frame S double prime. Right, last part, which of the frames is inertial? Well, S and S prime are inertial because it's satisfies the motion of the puck, satisfies Newton's first law, the law of inertia, whereas S double prime does not. So S double prime is non-inertial. And that's it. Like I said, there wasn't that many questions in this section, so kind of a short video for this one. But that means we can move on to 1B in Axler, which I'll do within the next couple of days. Hopefully we'll be able to get another round in for Spivak before the holidays swing around, but I'm not confident in that because I have a bunch of stuff that I got to do for work this week. So we'll see. But anyway, I'll see you guys in the next video, which we'll do section 1B in Axler, and then after that we'll have to do some problems from section 1B. So I'll see you guys in the next one.